So, good morning. Good morning to everyone. So it's my genuine pleasure and distinct honor to introduce and to present you today the talk of Prabha. The typical academic introduction would require me to just tell his CV and all his achievements in professional and scientific life, but this clearly would be a daunting task. Actually will lead me to a miserable failure. So today, actually in these days, I decided to take a totally different route. And so I like to share with you one note and one thought that I would like to share with the young students that are here. The first note is that I think that this seminar can mark today the launch of a new series of seminars that we would like to offer in the Scuola Sant'Anna about the future of AI. And so we would like to involve in these seminars many prestigious international speakers that will come here and they will convey what they are their thoughts about the future of AI, not only from a technological point of view, this is a part, but mainly because of the nature of the school, about the societal, economic, health, and legal implications that AI can have on our society and our life. And we hope that this series will offer to all of us a moment to reason about these evolutions, this transformation, and also which are the perspectives and give us also inspirations about this topic. And what is important, and I actually like very much, try to build bridges between the numerous interdisciplinary researches that are done inside the school and the research groups of the speakers, their companies, or their organization. And I think that in this context, if we think to the transformation that is happening in those days, actually there are people that have shaped this transformation in terms of innovation, strategic view, and research achievements. And it is not only my thinking, but I think that Prabha is one of the people that have shaped all this stuff in the last years in search and artificial intelligence, so it's an honor to have him here at the school. The second thought is just a consideration that came to my mind thinking to this talk, and I just added this morning. It's a personal note, it's an anecdote about my life. I knew Prabha in the mid-90s, so more than 30 years ago. I was a PhD student in the University of Pisa, and my mentor, Fabrizio Lucio, invited him to come to Pisa and give a seminar. So nice, Fabrizio, to be here. And at that time, we were listening the talks, and I always admired actually the elegance and the humility of Prabha. This is something that qualities that you never changed in these years, even if your career have traversed the sort of impressive results, scientific and professional results. So this is something that I continuously admired of Prabha. He was always, I'm a witness, he was always able and available to meet students, to meet young researchers, to talk to them in any moment, in any time. And this is something that I continuously say to my students, that he's an example of what scientists and gentlemen should be in our community. And actually, this is something what research should be. Because I think that research, first of all and foremost, it's collaboration, it's exchanging of ideas, exchanging of perspectives, and also is inclusion of mainly up to now people, in sense of without any bias and without any limitation. But I think that with the talk of Prabha, we will make a change in the sense that in our research groups, we will not have only to include people and be not biased with people, but we have to include AI tools. And this kind, I don't know if you will agree with me, but we will discuss at the end of this talk. But I think that this will change our position because we will have to see what is our role inside the groups when AI will enter. Prabha will talk about the experience in DeepMind. But I think that what is important is that, in my opinion, in the next years, we as humans will be more and more required to increase our intellectual bars, will increase our inspiration, our creativity, and our way of interacting with the machine. So it will be not an easy time for us. Our life will be not simplified, but as researchers, we will have more higher goals to reach. So let's discuss at the end, after the talk of Prabha, if I convinced you or not, and if you agree with me. So thanks very much to be here. Please enjoy the talk, and it is a pleasure. And I can say that Prabha accepted the invitation to come from US to Pisa without any hesitation. So it's a full honor for us to be here at the school. Thanks very much.
Thank you. Good morning. Can you hear me at the back? Okay, good. Before I start, I want to get a sense of the audience. How many people here consider themselves to have a background in computer science or mathematics? Okay, a little less than 50%. Okay, good. I will try to make this lecture accessible to a broad audience. The first 10 or 15 minutes is very non-technical. It's more or less common sense. Then the next 30 minutes will be the more technical part, but I will still try to make it accessible to non-mathematicians. And then again, at the end, the last 10 or 15 minutes will be reflections. Okay, you want me to lean forward? Yeah, good idea. Okay, this should be better. Yeah, I don't know why I have to be raised. So I'll try to make the whole thing very accessible. So the focus of what I set out to do was to try and understand the role of AI in discovering new science. Okay? But before that, I want to start at a very classical place. This is Alan Turing's paper from 1950, where he started setting out a notion of an imitation game. There's a movie also called The Imitation Game. I don't know how many people here have seen this movie. Some of you have seen this movie, correct? So in the movie, you see this Turing figure who sets up this task that says, behind a screen, there is something you're talking to. And it could be a human or it could be a machine. And the challenge he threw out was, can we build a machine that will fool you into thinking it's a human, right? And this was this classic paper that he wrote in 1950, and this is the beginning. And in it, he, I think for the first time, tried to challenge us, what does it mean for a machine to think, right? Okay, so we did this, and now we've had many striking successes that push the boundary of this test, right? You have chatbots, and by some standard, chatbots already pass the imitation game, okay? You have striking successes in AI, like self-driving cars. So I don't know if anybody here has been in a Waymo or a self-driving car. Okay, if you go to San Francisco and now many other towns in the US, just like you can call a taxi or Uber using an app, you can call a Waymo, and this thing shows up, there's nobody driving it, and it takes you to your destination, right? But there are also some very serious and significant scientific advances thanks to AI. The best known example perhaps is protein folding, where about 200 million proteins of interest to humans were folded. The 3D structure was determined by my colleagues in DeepMind, and this won a Nobel Prize earlier this year, right? Math Olympiads, AI is reaching championship level performance. And so you look at this and say, okay, not only did we have the imitation game, we have something much more general, okay? But then, those of you who have dealt with chatbots, with LLMs, find that it will still make rudimentary, simple mathematical errors. So even though it can somehow attain champion level performance in an Olympiad, it can make mistakes in elementary addition and subtraction, right? And so you start to think about what does it mean to have general intelligence from a machine? And people come up with all sorts of definitions, and I'm going to point out to you why this is difficult, okay? So people say, well, we want machines that can do everything as well as the average human. Okay? Is that a good standard? So let me challenge you. Suppose you're going to have an AI robot performing a surgery on you. Are you happy with the standard of an average human? Would you want an average human? Who here wants an average human performing a surgery on them? Nobody, I think, right? So what it starts to say is that the notion of performance in a task actually depends on the task. It doesn't just depend on some notion of average. So I want you to go through a thought experiment. Suppose you have an AI-powered robotic surgeon operating on you. What standard would you insist on? Okay, self-driving car. Okay, or even something with less dangerous consequences, like if the AI system is booking travel for you, what is the standard you would hold it to? Okay, now this question was already explored in a paper by my colleagues Meredith Ringel-Morris and others, and they said, wait, we have to think of two simple questions. When we say the AI is better than which human, right? Average human, no, right? Are you happy with a surgeon that is better than 99% of humans? Probably not, okay? So we're going to explore this in a second. And then it depends on which task, okay? So this picture has a lot going on. So let me try to walk you through it, right? So on the circles, you see powers of 10, right? And I claim that roughly, order of magnitude, about 1 billion people can drive a car today in the planet, okay? Roughly 100 million are people in so-called white-collar professions. These are professions where you have to interpret complex documents, lawyers, doctors, professors, etc., right? The number of people in professional software development is about 10 million. About 1 million people have earned a PhD in a STEM field, and so on. If you go all the way to the left, I would say there are maybe 10 or fewer people who are capable of proving Fermat's last theorem. Only one did, actually, and I don't think Fermat proved it, but we don't know, right? So, okay, so we look at that, and then I ask you to think, and for the two curves at the bottom, there is no y-axis really, but it's really a relative way I want you to think about it. The green line is what would you consider an acceptable standard, okay? What is an acceptable standard that you would insist on for a machine driving a car? What is an acceptable standard for proving Fermat's last theorem? I think that is clear. The proof has to be correct, otherwise it's useless, right? And so this curve jumps up and down. And then below, I give some representation. Again, this is not sort of numerically accurate of what current AI models are capable of, right? And the gap is pretty large towards the left, but in some cases towards the right, models are getting very competent, right? And the thing I want you to think of is because we see decent capability in driving cars, in interpreting documents, maybe in some aspects of software development, we get very excited and say we can do everything, right? The reality is we won't, and what we'll talk about in the central technical section today is some very early work on what it will take to prove theorems using AI, okay? But I call this the jagged landscape because really what you need varies by task. And in your own mind, I want you, as you look at that circles on the top, think of your own task and think of what is an acceptable standard and where models are today. And it's a very useful exercise, right? And so the simple notion of artificial general intelligence doesn't hold. It really depends on what task and what is the standard, right? Does it make sense? Okay. This should be accessible to everybody. This is not technical, right? Good. This is common sense. And as informed citizenry, we should be thinking about this, especially because people are running off to regulate AI and make policies and so on, right? The landscape is actually tricky. That's my point here. Okay? All right. So now, many AI artifacts today, whether it's chatbots, recommendation algorithms, et cetera, they have some measure of upside. How happy does it make people? Okay, in the case of recommendation algorithms like Amazon, how many products get sold? These are all measures that are used to improve the algorithm. Okay? And that is some proxy for goodness. Okay? But then you add guardrails for mitigating harm. That is roughly how it works. We don't have a good way of pricing the downside. Whereas if you're driving a car, I think there's a clear notion of, well, there's a downside. If it gets into a crash, it's bad, right? Statistically, self-driving cars like Waymo today seem to have fewer crashes than humans based on many tens of millions of miles of driving. So that's a good start, okay? So let's go back to the questions we asked earlier, right? So what's a good standard for a robotic surgeon that is about to operate on you? I claim it has to be better than the best human that you have access to, okay? This is my claim, but I want you to think about it, right? A flight booking system, you can say, well, it shouldn't make more than one mistake in a million bookings. Now think about it. Every day, the world has tens of millions of bookings, okay? And hopefully most of those are correct, right? A self-driving car, now this is an interesting one. I claim it's rational for you to go in a self-driving car, provided it drives better than you do, okay? Now, of course, if you take surveys of population, most people think they're better than average drivers, so that's slightly problematic. But you get the point. You can start to put guardrails and benchmarks on what it means for good sense, for common sense to, okay? Now, by task, you can start to think about, you pick your own favorite task, what makes sense. Okay. Now, the last thing I want to say on this general section is there are, in fact, problems that are computationally intractable, meaning nobody, no AI, no computer can solve them. So this is due to work by Kurt Gödel in 1936, when he basically said that in mathematics, you cannot insist on self-consistency. And Alan Turing then took this to say there are essentially programs nobody can debug, okay? So if you're a venture capitalist and somebody comes and says to you, I have an AI that writes perfect software, you should say, no, I don't believe you, okay? This is actually beautifully detailed in a book called Logicomics, which is by Christos Papadimitriou, who's a friend of many of us here, right? And I really think that this is something to keep in mind. AI is not going to do everything. There are things that are beyond even AI, okay? So you can compare AI to humans. I'm not saying humans can solve the halting problem, but neither can AI, right? Okay, good. Now, I'm going to get into the technical substance of the talk, right? So here we are trying to use AI to discover new results in computer science. And this is work in the area of theory of computing, which is the specialty for some of us. This is joint work with Anj Nagda, who's a student at Berkeley, who's an intern with us, and Abradeep Thakur, who's a scientist at DeepMind. And the three of us recently released this paper. So let me tell you about this work, okay? So the question we ask is, can AI assist research in this area, in the theory of computing? Which is not the same question as, can AI do something that we could never do as humans? Because, as I will argue again at the end, I don't know how to tell you that a human could never have proven a theorem that AI proved, okay? And this is in itself a difficult problem, right? But the reason we wanted to study the foundations of computing is if we can do this, we can apply these methods to other areas of computing, okay? So the particular sub-area that we're going to look at, we started thinking, how could AI help in scientific research? Now, when I say AI here, I'm mostly talking about language models, the kind that many of you have interacted with, right? So one thing you could say is, I want to prompt a language model to give me an approach to solving a problem, okay? So for instance, you might say, my background is topology. There is this field called Ramsey theory. I don't know anything about it. Give me an approach to taking my skill to attacking problems there, okay? You can say, let's fill gaps in a human proof. So there's a celebrated mathematician at UCLA by the name Terence Tao. Some of you may have heard of him. And if you listen to this podcast with Lex Friedman, he'll say, well, human mathematicians, they write out long proofs of things, but they leave out many details, and the AI can fill in the details. That was Tao's view of how to do it, right? What we do is use a tool called AlphaEvolve that I will describe. This is a tool built at DeepMind, okay? So the idea is you have a proof of a theorem, and what AlphaEvolve will do is take a piece of it, try to improve it, and you test if it's good, and try to improve it and try to improve it, and hopefully you come up with a better theorem. Okay? And I'll describe this process in a little more detail. Okay? So this is the Terence Tao approach, right? He says a proof is some long string that some mathematician has written out, but they left out some details, and AI will go and fill in the details, say, okay, this is true, but it's painful to show. This other thing, maybe it's not true, etc. Right? So what we're doing is slightly different, right? So AlphaEvolve, again, is the name of this tool. What it does is it takes this long string, which is a proof, and picks out a specific piece, and then replaces it with a new piece. Those of you who are used to gene editing, you can think of it as a very similar move, right? With tools like CRISPR, you take out a piece of a gene and you replace it with a new piece. This is very similar in spirit. We take out a piece of a proof and put in a new piece, right? And the nice thing is the rest of the proof is intact, provided the original proof was correct. All you did was to improve this little piece, and so you have a better result, okay? So far, so good? Good. All right, so what is this AlphaEvolve, this tool that came out of GDM? Okay. What it's going to do is improve a little piece of a proof. How does it do it? What it does is it generates a bunch of Python programs whose job it is to write a better piece of proof. Okay? I'll call it a chunk. So these programs generate new chunks. They take the old chunk and say, put this in instead. Okay? And you score the chunks by some criterion. We'll talk more about this. And the programs that are more successful are fed back into the LLM, and new programs are generated. The programs that did not succeed, you throw them away. Okay, so it's this evolutionary approach. But the evolutionary approach is not directly working on the proof itself. It's working on these Python programs that generate pieces of the proof. Okay? And this turns out to be crucial. Okay? So that's what AlphaEvolve does. It's the name of the thing's called AlphaEvolve. Okay. Now, the particular area I'm going to focus on is what we call discrete optimization problems. Okay? So, what is a discrete optimization problem? A classic example is the traveling salesman problem, which I'm sure many of you have heard of. The traveling salesman problem, you're given a bunch of cities, and I was promised that Pisa was one of the cities that was picked here, right? And the salesperson has to visit all n cities with the shortest tour possible. Okay? So, you're given all these cities, and the program has to go away, come back, and say, I found a thing that goes through all the cities and comes back, and it is 1,000 kilometers long, and that is the best possible. Okay? Unfortunately, in this case, finding the best possible is pretty hopeless. Okay? So now let me give you sort of a 30-second or 2-minute version of the notion of efficiency versus intractability. And those of you in computer science, this will make intuitive sense. If you're not, it will take a moment, so stay with me, right? So essentially, the field consists of taking any problem, like the traveling salesman problem, and putting it into one of two buckets. One bucket has problems that are efficiently solvable, like sorting n numbers, it's efficiently solvable. The other bucket is problems that are considered intractable, as in there is really no efficient algorithm to solve them. What does it mean to say no efficient algorithm? Essentially, you cannot solve this problem without trying all possible ways of visiting the n cities. Okay, now if you have 50 cities, the number of things you have to try has 64 digits in it. It is basically hopeless, right? And so the traveling salesman problem and many, many, many other problems, including the one that I will show you next, is widely believed to be intractable. What do I mean by widely believed? Mathematicians have said, if it is not intractable, then a lot of mathematics will collapse. Okay? So therefore, if you believe that modern mathematics is well-founded, then we believe that the traveling salesman problem is intractable in the sense that there is no efficient algorithm. An efficient algorithm takes an instance of the problem, with say n cities, and solves an n to the k steps where k is a fixed integer, like n squared or n cubed or something like that, right? Then we say it's efficient. If we don't know how to do that, then you have to try every possible solution. That's too many. Okay? So in theoretical computer science, the foundations of computing, there is this dichotomy, things that are efficiently solvable and things that are difficult. Okay? And we will focus on problems that are difficult. Okay? Now, how do you cope with this intractability? Okay? There are essentially 3 branches of work, and we'll look at 2 of them. The first is to say, Well, we don't know how to find the shortest traveling salesman tour, but we'll find a pretty good tour. I'll find one that is guaranteed to be close to the best, okay? So, I was telling you of this example. Let's say the shortest tour is 100 kilometers. We don't know how to find it. What the approximation algorithm says, never mind, I will still find you one that is not more than 150 kilometers, so 50% more. Right? Now, that seems like a big slack, okay? But that is a guarantee it delivers. And so for the traveling salesman problem, such an algorithm exists that gives you no more than 50% overhead, okay? The second is to prove that no efficient algorithm can come close to the best, okay? So for the traveling salesman problem, we have theorems that say no efficient algorithm can do better than 1% of the optimum. So if the best solution is 100, we say, well, it's hopeless not only to find the 100, it is hopeless to find even a tour of length 101. Okay? Now you look at that and say, that's pretty terrible, 1% versus 50%. But that is the state of the art. And so what we do in the field is to constantly try and squeeze this gap down between what is doable and what is impossible. Okay? And so you can try and improve on the 50%. We tried, we failed. And you can try and improve on the 1%. And in the case of the traveling salesman problem, we are still trying. We haven't improved this. Okay? I will talk about a different problem in a moment. Okay? The last approach is to say, well, maybe the worst case instance is very hard to deal with, but what if the instances are random? The cities are randomly chosen from all over Italy. Okay? Maybe that makes it easy. So we will talk about these two buckets of results. But as I said, we failed to make any progress on the traveling salesman problem. So here's the problem that we look at instead. Right? It's called the max cut problem. So you're given this graph. In this case, this graph has 14 nodes. Those white circles are the nodes, and you're given some connections between them. And the max cut problem says, I want you to break this graph into two pieces while cutting as many of these connections as possible. Okay? Now, I say as many, because if I say as few, it turns out to be pretty easy. So let's look at this example. If you cut the green edge, right, then by cutting one edge, you've broken it into two pieces. Okay? But if you want to cut many edges, maybe you have to go through the red cut. In fact, you can do other cuts that break it into two pieces. And that turns out to be hard. Okay? Now, you can study the more general piece, where you don't cut into two pieces, but 3 pieces, 4 pieces, 5 pieces. This is called the max 3 cut, 4 cut, etc. So we'll study this family of problems, and I'll show you what we are able to do with AI. Okay? So everyone understand the max cut problem? You want to find a way of breaking the graph so that you're tearing open as many connections as possible. And intuitively, I want you to think about it. This turns out to be quite a hard problem. Okay. Now, you could ask me lots of questions. Well, what did you actually prove? Okay. How did you do it? Well, I gave you the hint. We used this thing called AlphaEvolve. And then I think the deeper question, which we'll come back to towards the end of the lecture, is, did you really need all this AI? Did some smart human have come? And to me, that is a really interesting question. So, warning, I will take you through some very technical results, but it, in some sense, doesn't matter exactly what those technical results are. What I want you to start thinking about it is, did AI matter, right? Is AI really helpful in proving these new scientific results? Or, we don't know, okay? So we'll get to what did we learn in the process, what are some reflections. Okay, so we have two results, okay? First, we prove that max 4 cut, the problem of breaking a graph into 4 pieces, is hard to approximate better than 98.7% using AI to find a novel gadget reduction. I'll explain in a moment what a gadget reduction is, okay? And then the second result we have is in the random graph case. So you have a graph, every node is connected to 4 random neighbors. It is mathematically unlikely that you can certify that the cut breaking into 2 pieces is close to optimal, okay? Now, these are very technical statements. I will get into them in a little more detail in a second. But both of these, it turns out, are new results that humans and mathematicians did not have before, okay? So we were able to use AI to get these new results that had not been proven before, okay? And later in the talk, I'll give you a comparison to what was known before our work, okay? So what humans had been able to do, And, just a spoiler alert, we have slight improvements on what humans did. These are not massive improvements. This is not Fermat's last theorem. So that's the warning. But I will also argue that it's unlikely that humans would have found what we found. Okay? Of course, time will tell. Okay. So this is the first result. We prove that max 4 cut is hard to approximate better than. So in other words, not only will you not find the biggest cut, you will not even find one that is 98% of the biggest cut. Okay? That is what we're saying. Okay. So what's a gadget reduction? And so this is the technical part of the talk. So stay with me, right? So typically the way you prove that something is impossible to solve is to start with something that you know is impossible and then construct a case of the target problem, in our case, max 4 cut, and say if you could solve this, then you could solve the other one. But we know that's hard, therefore it's unlikely, okay? So the particular source problem we start, which is known to be hard, is something called 3 ln 4. And the idea is you have a bunch of equations. These are equations mod 4. So everything is 0, 1, 2, or 3. They're modular equations. And the right-hand sides are all 0, 1, 2, or 3, right? So you have this family of equations, and we are going to use that to build a graph and say that if you can cut this, then you could have solved that, okay? I won't take you through all the details, but just to give you an idea, so that's called a reduction. And the particular piece of it, it's called a gadget, is to build this graph up piece by piece. So you take one equation and use it to build a piece of a graph, okay? And that is called the gadget, okay? And we're going to use AlphaEvolve to find this gadget, okay? And I'll show you a picture of the gadget that is found. And you do this now for all the equations. You built up a big graph, and then the argument is if you could cut that, you could solve that, which is impossible, therefore you cannot cut it. That's really what we're doing. Okay, so here is the gadget, okay? I'm going to ask you to believe me because I'm not going to prove anything about it. So AlphaEvolve worked for many days and came back and said, this 19-node gadget takes an equation and builds a piece of graph, and for every equation, you build a piece of graph in a similar fashion, and you end up with this big graph. And the theorem basically says, you cannot cut this efficiently because then you would have solved that problem. Okay? So that's really what it is. Okay? Now, you should say, why should I believe you? How do I know it's correct, right? And this is a persistent theme towards in any AI-generated object, including a chat response, right? Something comes back at you. Why do you know it's true? Okay? So, how do we know it's correct? Now, it turns out that this requires something called verification. So we have to verify that mathematically, this thing on the right is equivalent to the thing on the left, right? And that requires a computer program because there are so many possible cases to try here, okay? So, but to summarize, what we did was we took somebody's theorem, which had a long proof. They had a gadget, and we replaced their gadget with our new gadget, and that gives a new theorem, right? So that's really what is going on here, right? Now, this verification that it's a valid gadget is slow, but one of the things we were able to do is we were able to use AlphaEvolve to speed up the process of verification itself. So AlphaEvolve gave us a faster verifier, okay, without which we could not have come up with this result. So AlphaEvolve played two roles. One is to generate this gadget, and second, to prove that it's valid. Okay? And AlphaEvolve did both for us. Okay? Okay. Now, it's crucial to note that I showed you this gadget, this little piece of graph with about 19 nodes, but the result, the theorem, is not about 19 nodes. It is saying for every n, this hardness holds, that you cannot, it's hopeless for you to find 99% of the best possible, right? And for those of you who care, this is the formal theorem statement from the paper, okay? This process of going from a fixed size object, in this case 19, to a theorem that holds for every possible n is something we call lifting, and it's a theme. So in other words, the theorems you're proving are universal. For all n, they're true, even though there exists something of size 19 in this case. Later in the talk, you'll see a case where the thing we find, the object we find, is much bigger than 19. Okay? All right. So how does this compare? It beats the best known previous result by 0.1%. And I know your reaction should be, what, you did all this hard work, and you came up with a 0.1% improvement? Two things. So first of all, in this area, progress is very slow. It takes, this is like 10 years old now, right? It's a 2014 result. And so the world of mathematicians is slowly squeezing out progress, and we squeezed out some more progress here, right? But to me, like I said, and I will keep repeating this, it almost doesn't matter whether it's 0.1% or 0.00001%. The fact that makes me excited is the how, and the how is to use an AI tool to get a result that we were not able to get before. Okay? Okay, let me quickly run through my second result, which says, for a random graph where every node has 4 neighbors, it's mathematically impossible to certify that you can cut optimally. Okay? Now, this builds on more recent work from last year, and it requires us to build through AlphaEvolve. Remember, I built this gadget in the last example. In this example, we have to build something called Ramanujan graphs. Okay? So I won't get into the mathematics of what a Ramanujan graph is, etc., but I'll give you a flavor for what this took. Okay? Okay, so why are we studying this? We said, well, these worst case instances are hard. Maybe random graphs are easier, right? So we're looking at the max cut problem on random graphs where every node has 4 neighbors. Okay? And what Kuniski and you showed last year is that, on the one hand, with high probability, the max cut in such a graph has about 1.7 n edges in the max cut. Okay? And they showed that you cannot get a certificate better than 1.75. So in other words, computationally, you cannot get close to the best possible. That is the result. Okay? And the main idea is they found a 10-node Ramanujan graph. So the central piece of their proof was something called a Ramanujan graph with 10 nodes. Okay? What we find is we were able to raise that 1.75 that you see here at the bottom of this slide to 1.82. Okay? So on the one hand, this seems okay. Not a bad improvement from 1.75 to 1.82, better than my last example maybe. But also you can show analytically that this is pretty much the best you can show. Okay? So this is a significant piece of progress. How did we do it? Right? So in this case, we took that piece of proof, the 10-node Ramanujan graph, and we built one with 130 nodes, roughly, right? And finding a 130-node Ramanujan graph is actually interesting in its own right for people who study this field. Okay? And AlphaEvolve also gives us a verification that this object meets the criteria. Okay? So this was the graph. I don't expect you to look at it and get any amazing insights, but you know, this exhibit is in our paper. You can go look at it. Okay? So this is a message I got from Paolo. He said, don't show any proofs. This is a message he sent me, so I'm not going to show any proofs, right? But I will give you a couple of final details of what it took to get there, right? So we were able to study this problem. We also studied a different problem. For those of you from computer science, it's the maximum independent set problem. Again, certifying these in random graphs is hard, and we improved that. In that case, we had to find a Ramanujan graph with 163 nodes. Okay? Okay, so this is sort of a summary of the results. We improved a whole family of them from the Kuniski paper. And if you read our paper, you can see. So many of the improvements are not only significant improvements, they're close to the best possible. So for instance, if you look at the bottom row, the 0.457 is the best you can prove. 0.454 is what we were able to get to. Okay, okay. So this is the reason this is. Let me sort of wrap up the technical section, and then let's get back to reflections. Right. So Kuniski also used computer-generated computer programs to generate Ramanujan graphs. We did. We couldn't use their approach for a couple of reasons. Once, as n goes big, the number of possible graphs becomes much bigger, and the good Ramanujan graphs that we need become very rare. Okay? And showing a large cut or independent set is computationally too intensive. So what we actually did, we didn't only ask AlphaEvolve to find a better graph, but we asked it to find a better graph with a better cut. Okay? And that's what this is. So we said, AlphaEvolve, go find these graphs with a big cut. If it's not Ramanujan, score it minus infinity, otherwise give it a good score. And it kept improving the score. All right. So let me finish with a few remarks first on AlphaEvolve, but then stepping back to what is the role of AI in scientific discovery, such as this. Okay? The first thing I said, and you must have caught, was we have to point AlphaEvolve to improve something, right? It requires some notion of goodness, and I gave you this example, right? How good is this proposed gadget, right? And you have to assign it a score, even if it's not valid. How good is this Ramanujan graph? And this choice of score was a lot of human intervention. It took a lot of expertise. In fact, one of the people who first reviewed the paper said to us, okay, I'm not surprised because you people know this area very well. You're experts in theory of computing. So you can do this, but not anybody. And indeed, I agree, right? So it is very sensitive to guiding this tool in the right direction. And you need a lot of domain knowledge and insight and intuition to be able to do that. Okay? The second thing, and this is a recurrent theme, in any AI-generated artifact, you need to verify that it's correct. It's serving your purpose. It is proving your theorem. If you're talking to a chatbot, if the chatbot says something, you need some guarantee that it is saying the right thing, right? And this verification problem is often at least as hard as the original generation problem. Okay? So we did use AlphaEvolve to speed up the verification process. And indeed, for the problems we were looking at the sizes we were looking at, AlphaEvolve actually improved the verification by a factor of about 10,000. Okay? So it made a significant difference, without which we could not have done this, right? So in some sense, guiding the generation and speeding up the verification are twin pillars that it takes to do this kind of work. Okay? Also, AlphaEvolve will cheat. Okay, what do I mean by that? Okay? So here in this rectangle, there is this block where we say, AlphaEvolve, we want you to find a graph with 58 nodes with some property. And you say, evolve. And the first thing it did was to change 58 to 40. Okay. And then it found it. And we're like, wow, that is quick. And then we realized it cheated. So if you're not very, very careful, it will go and evolve the wrong thing. It will change your problem, rewrite your problem, and then find a solution. But it's a useless solution. Okay? So you have to watch that it's not cheating. And it took us, and I will say, having worked on this now for some months, even recently we got fooled, because we would wake up one day very excited, find something and say, wow, we made big progress, we proved a famous result. Actually, we didn't, right? It was AlphaEvolve cheating. Okay. So what are the norms by which we should look at this work, right? So obviously, are the results new and correct? That is the base standard for any science, okay? But then you ask, what is the role of AI in this work? Okay? So let's think about both, right? Now, let's go back to how can AI help the scientific endeavor, right? So before you start your research, a language model can summarize the state of the art. It can suggest approaches to proofs, right? And we tried this. We tried many natural attacks on these problems. And we got, in many cases, very useful, but not always correct summaries, right? Sometimes a language model will give you nonsense, saying you should try this approach and this, right? And we found, for instance, language models love quantum anything. So no matter what problem you're trying to solve, it say you should try quantum theory. And you're like, okay, that doesn't sound relevant, but you get such suggestions, right? But I still think this is going to be an important facet of science going forward, because if you're in one field and you want to come up to speed in a different field, the language model is a very good way of introducing you. So expect more scientific cross-pollination over time, because experts in one field can go to a field where they're not an expert and learn about it quickly, right? I will say that we could not succeed in generating any useful proof strategies from an LLM, but that's not to say it cannot be done, right? Now you can go to LLM and say, write me a better proof. I demand you. There have been some reports out there that this sometimes works, but I don't know of an instance where this is robust. What I mean by that is, yes, an LLM can say, I can change this proof a little bit, and then some human comes and say, I could have done that, in 5 minutes, right? I don't know of a case where an LLM managed to do something that a human didn't come along very quickly and say, I could improve that. In our case, we could not get this to work. Okay? So then you look at our results and say, could a talented human have produced these results, right? And we used to joke, if you took somebody who was a real expert in these areas, in these gadget reductions, and locked them up in a room with nothing to do for 6 months, maybe they could have come up with this, because they start to see some symmetry in the way they gadget. But really, for me, the test is the test of time, right? I do expect that some human will come on and replicate or improve on these results, and I think that's a good thing. But how long it takes to do that is some measure of by how much did we beat the state of the art, right? You could also say, who cares about AI? You work at Google, you have lots of computers. Maybe you should have used the computers in a smarter way to come up with this, right? And it's hard for me to give you a proof that there is no better way, okay? So I'm not going to claim that AI is somehow absolutely indispensable. But what is nice is a tool like AlphaEvolve is a generic tool. We were able to apply it to a couple of problems. You're now attacking other problems. So we don't have to write custom tooling and programming for every problem we're attacking. So that's one nice thing. Okay? So the claim I'll make is that simple pencil and paper with a human would probably not be able to replicate these results, right? If we stand the test of time, then we have some evidence that this AI assistance was necessary. Okay? Then if somebody else endowed with lots of computing, could they have done it? Well, again, it's hard to give you a definitive answer, but I think tools like AlphaEvolve and others that my colleagues at DeepMind are developing have this promise of being able to apply to a wide range of fields and a wide range of problems. And so I do believe that these tools that can be reused across problem domains will have a role in the future of science. Okay? I'm not going to claim that we're anywhere close to doing something like Fermat's last theorem. Okay? And if you remember that picture I had with the jagged landscape, right? I said, today we have something like 1,000 humans who won Nobel Prizes. Okay? I would argue that the AI has already won one Nobel Prize, which is protein folding. Okay? Which is not to discount my colleagues, John Jumper and Demis Hassabis. I mean, two brilliant people. But I don't think they could have done it without the AI, right? So I would argue that gradually these AI tools will become more and more important in how we do scientific research. Okay? And that's the strongest claim I'll make. I'm not going to, you see these very sensational articles out there that say things like the next 50 Nobel Prizes will be won by AI. I don't know about that, right? I think human ingenuity is still at the core of it. But I think these tools will definitely give an advantage. And having generic tools like AlphaEvolve and some others that people are developing will be useful because you don't just use it for custom built for one problem. And this is, I found this interesting because if I talk to people in physics or the life sciences, they'll say, what are you talking about? We build a new apparatus for every project. For us, it's not new to build new tools. But the fact that these tools are reusable, I think is powerful. Okay. The last comment I'll make on AlphaEvolve is it had no idea what we were doing. Okay? We said, here is the score, improve the score, and it did. It didn't know anything about gadget reductions and interactability. It didn't know anything about Ramanujan graphs, right? We just gave it a score, it's improving. Now, one interesting program that we can pursue is to try and give the LLM inside AlphaEvolve more of an idea of what we are doing. Go read up all the literature in this area and use that to do the improvement. That's not currently in operation. There people have asked us, how much computing did you use? How much of your expertise did you use? And it's very hard to quantify some of these things. Like, I don't know how to quantify how much expertise I bring to the table, or my co-authors do, right? And while these are valid questions, I think they're premature. Our first beachhead was to say, we did new science with the help of AI. We don't think it can be done easily without the use of AI, right? We will know, we'll find out, right? And that's the stage we're at. Over time, we can think about efficiency and human expertise and the amplification we get. So some reflections, right? Where would these new results rank among the results of mine that I would be proud of? I would say as original research, pretty low, right? It's not my proudest result. But the significance to me is not what we did, but how we did it, right? And I think that is somewhat pioneering, right? So we do know that AI models with such feedback can generate fairly intricate mathematical constructions. And along the way, sometimes we found it doing really interesting things, manipulating equations and so on, okay? Language models can indeed generate research plans, but we couldn't get them to do new research. Okay. So what do we expect going forward? We expect a growing number of proofs and theorems of the form, well, AI did it first, right? And I had an interesting exchange with a mathematician, Jordan Allenberg, at the University of Wisconsin, who said, I don't care if a human gets there eventually, you got there first, and AI did it. And I'm like, okay, but maybe we did something trivial with AI that a human will also do. So that's an interesting question, but we will see more instances of AI did it first, okay? I don't think we will see arguments like this needed AI. Without AI, you could not, right? In all cases, we expect verification to remain the bottleneck across all uses of AI in science. AI will help do science, but verifying that it is correct science will be non-trivial and will require a lot of human ingenuity, okay? And so this leads to sort of what replicable methods does AI provide for assisting science? And this is one very narrow paradigm that we showed, but I expect more tools and more methodologies to emerge in the future. Okay. All right, so in summary, so I argued that the landscape of AI, of generality, is very jagged, and I was told that the Italian word is frastagliata. I don't know if that's true, right? So it's very hard to derive generality from it, right? We argued that AI can assist in different ways to pursue research in the mathematical sciences. And my colleagues at DeepMind have been looking at material science, climate, life sciences, and so on. And maybe we can make progress in those. Early results are encouraging, and you should expect to see more cross-pollination across disciplines. But it's still hard to get some sort of general result out of this. I want to close with the end of Turing's paper, right? And please bear with me because so much insightful commentary here, right? Turing says, we may hope that machines will eventually compete with men in all purely intellectual fields, but which ones are the best to start with, right? And in my jagged landscape slide, I showed you a bunch of samples that can be done by 1 billion people, 100 million people, et cetera, right? Many people think that a very abstract activity like the playing of chess would be best. And then he goes on to say, but maybe you should use supervised learning, teach the machine what to do, right? And I love his final sentence. It says, we can only see a short distance ahead, but we can see plenty that needs to be done. And that was 75 years ago when we didn't know anything about this field, and that is still true. So with that, grazie mille, thank you so much.
Okay, thanks very much. Are there any questions? Okay.
You mentioned like Ramanujan graphs, which are very good, I think, for exploration, because if I understood correctly, they have they are very well connected with very few nodes, links for each node. But real networks are more often like scale invariant or with very few hubs with with many links. In that case, did you find any other results, or is it easier to do with Ramanujan graphs?
Yeah, so the approach we've laid out actually works for denser networks also. We haven't done all the calculations in many of these cases, right? So the paper I cited by Kuniski and you in 2024 sort of lays out the program. They've laid out the results for sparse, dense, etc. We did the computations for 3 and 4. We got an improvement. We're pretty happy. I suspect that as we get to denser networks, our improvement will not be as impressive, but we'll still get some small improvement.
Yeah, thank you for a very inspiring talk. Maybe it's a bit of a sci-fi question. I apologize for that. But so you mentioned that this process can accelerate things, right? But can you fathom a case in which an AI can actually solve a theorem that a human cannot solve? And in that case, the verification process becomes much more complicated, right? So I get to the case for the life science, for example, you mentioned that, and also you can accelerate evolution and go in places where evolution didn't have the time to go.
Yeah.
But when it comes to theorems and building the theory, do you see a space there?
You know, based on the early work, I think we're very far from attaining that goal, right? So an example might be, could an AI resolve the Riemann hypothesis, right? That would be an amazing dream, right? When I see how much we struggle to even do the little bit of improvement here, I'm not optimistic we'll get there soon, right? But I have to share this with you. When I finished my PhD many years ago, I went for a faculty interview, and I was asked, what is your prediction about AI? And I said, in my lifetime, an AI will not beat a human at the game of Go, okay, which is a wrong prediction. AlphaGo beat the human grandmaster, right? So I was wrong then. My guess is I may be wrong again about this one. The standard that is difficult here is to prove that no human will get there. So one of the results that I mentioned, there were several. One of the results in our paper, after we got it, a colleague who's very talented went off and thought hard for a month and came back and said, I can do it by hand, and I didn't cheat, right? And he's a very good guy. So the standard of not feasible for a human is very difficult to establish, right? And in a weird way, these machines are kind of trained to follow human thought processes, but at scale. So the question is, will they get a creative spark, right? I mean, if you look at the proof of Andrew Wiles's proof of Fermat's last theorem, he brought together 3 or 4 disciplines in mathematics and made all these jumps between them, right? I have not seen anything close to that in a machine yet. It's a great question, and it's, I think, the defining question. And then the second part which you observed is, okay, even if you did it, who's going to verify this? And today there is something, some of you may have heard of an enterprise, an endeavor called Lean. Lean is a way of verifying theorem statements. But it is still so early and primitive that any complicated theorem is not going to get resolved by Lean yet.
Oh.
So thank you so much for making this available also for non-technicians. I'm from the legal background. I was wondering about the attributability of the kind of, let's say, some things like theorems that would be proved and stuff. So would you think that those who developed this kind of tools, like AlphaEvolve, should get some kind of, let's say, praise for developing this tool? And it's not, let's say, AI against humans, but it's human plus AI against humans without AI. I hope my question is clear.
Yeah, this question we keep getting asked, like, how much was it the AI versus what is in your head, right? And attribution in general in a scientific endeavor is hard, even without AI, because you build on centuries of work to do something. Now you have this additional complexity, right? Literally the only claim I can make is that we did something that A is new and B seems numerically beyond human thought, okay? Because, for instance, in that case of the 19-node gadget, the verification requires checking 2 raised to the power 2 raised to the power 19 things, which is like some big number, right? But then maybe somebody with a brilliant insight could say, okay, really, you could do a lot of that without using a machine. So I'm not able to tell you that we deserve more of the credit or AlphaEvolve deserves more of the credit. I can tell you that this style of work is not something I'm very familiar with, so I do not bring a lot of expertise to it, and also for my colleagues, it was a little new. But despite not being from this very narrow subfield, we were able to make progress. Okay, so that's all I'm able to say.
Thank you for your exploration of AI in math. So what you talked about is a very specific field. Do you think AI is going to get better and better at exploring very specific fields and so becoming a tool to be used in such fields? Or is it going to get better at general understanding? And so as such, as it better envelops human reasoning, be better at specific tasks that way?
This is an interesting question. So we have a small number of examples. In this case, I would say we were 3 computer scientists who have some understanding of what software can do, what AI can do, and the target domain of theoretical computer science. In the case of protein folding, John Jumper spent a lot of time understanding the 3D structure of proteins and what is there in the protein data bank before he started with AI. So my takeaway from that is you need this confluence of people who understand how to sort of twist the AI tool, but also the domain knowledge. And that takes hard work. So to see this repeated across multiple domains, I think you need people who are willing to invest, either from the domain side, willing to invest in what the tool can do and how to adapt it, or the tool builders who are willing to understand the domain deeply, right? So it's not by any means a turnkey enterprise where you just take a problem, throw it into the machine and wait. No, in fact, we had many disappointments, we had many things we had to adapt. And just to be completely honest, I gave you 2 results in one narrow domain. At this point, we've tried across mathematics and computer science probably a dozen or so different problem domains. And so far, we have not succeeded at anything else. Okay? And we've been at it for about 8 months. We hope to get more successes. We hope this becomes a more replicable process. But I'm not yet able to declare to you that I found a formula that I can now take to many domains.
Hi, thanks for the talk. So for this lifting, this generalization from 19 to n, this is something I didn't catch. Was it done for was the AI doing this or the human? And also, how good are AIs into this generalization problem?
Yeah, this is a fascinating question. The lifting we took for free because the existing proof already did the lifting for, it was a gadget of size 5 or 6. And we took that out and put in 19. So essentially, we did the gene editing. And AlphaEvolve is able to find these finite objects, size 19 or 124 or whatever, okay? It's very hard to find a proof technique with AI that is able to reason about for all n. And the reason is then you essentially have to chain together logical sentences. And that is a fairly difficult thing. I'm not saying it's impossible, and maybe AI will get there, but yes, you're correct that the lifting is the critical part that makes this, into a real theorem. And we take no credit for that. That was already there, right? And the AI had no role in it.
Other curiosities? I have a last question. You were talking about replication of the result, but this kind of result requires a lot of computing power.
Yeah.
So even if this system is available, how can we use in another context that are not Google or other big companies?
I think you're asking a very broad question, right? Like, you are lucky to work at a rich company with lots of machines. But what about us at a university who don't have, right? One of the paradigms I'm optimistic about is when you could have asked that question in a more nasty way, which is you got this tiny improvement, and what was your carbon footprint for doing this, right? And I think in all these cases, the first time we break one of these barriers, we do it in a slow, painful, expensive way. And then over time, people get very smart about squeezing out efficiencies. The process we went through was inefficient in two ways. One, the algorithm itself. I said we got a verification improvement of 10,000x, but before we did that, we burned a lot of cycles, okay, getting nowhere. So that can be improved, and that will be improved by others, not necessarily us. But the second thing is, I hope I was able to convey that in some sense, we were shooting in the dark at many problems with no idea why the approach should work on the problem. And we had many failures, okay? And over time, I think we'll get smarter about which tool to bring to bear, right? So the combination of the two, I think, will bring this kind of result within the reach of university researchers and not only the privy of somebody in a big, rich company.
Thanks again, the speaker. Thanks.
Thank you all.